Okay, so one of the first things we need to do for a PVA is to establish how many trials we're going to run. Because as Jed demonstrated, he illustrated one trial, one random number, and one trajectory through time. And when you run a PVA, every time you press these random numbers, you generate a new trajectory. And what your goal is to run a fairly large number of these trajectories and then summarize the results at the end. And that's what we're aiming for here. Down column A, we set up trials, and these trials stretch out to the number 500. So you can enter as many trials as you want, but don't enter more than 500. And you'll enter that number here. And just so we can see our trials, we're going to enter the number 5. You also need to specify how many years you want to run your population dynamics out for. So if I wanted to make a statement about the probability of wolf persistence in 20 years, then I would enter the number 20 in cell G7. And in fact, if we look at our spreadsheet, you'll see that the maximum that the spreadsheet will do right now is 20. Of course, you can feel free to modify your spreadsheet and make it run out as far as you'd like to. So we're going to just say the number 10 for now. And the threshold is something that we have to specify as well. And I'll get to that in just a second. So with this information here, we're able to set up our population viability analysis. Down column B, we want to know if trial number 1 counts toward our result. And we're only going to consider 5 trials, but we want to set up an equation here so that trials 6 and up will have a count of 0, meaning they're not counted in our result, and that trials 1 through 5 all have the number 1 here, just to signify that we're counting those trials. So we need a formula in this cell, B17. It's just going to be an if function. So we'll find if. Remember, this has 3 arguments, and we're just going to ask, is the cell to the left of where our cursor is it less than or equal to, so you can combine those, the number of trials that's in cell F7, and we'll anchor the F7. If it's true, and you can see here the spreadsheet's returning the word true, we'll enter the number 1, and if it's false, we'll enter the number 0. And we'll click OK and double click that through, and so you can see here that the count now reflects this trial counts, this trial counts, these trials count. 6 on do not count because they exceed the value in cell F7. Now, our first year in our PVA is simply going to reference our starting population size, and we'll anchor that and copy that through. So the benefit of setting up your spreadsheet this way is you can change these entries in green, and the spreadsheet will automatically be updated to reflect these changes. Now this equation in cell D17 is perhaps the most critical equation. Here's our population model. In this cell, we're going to be entering the equation that will give us the number of individuals in trial 1 in year 1, given that there are 84 individuals in year 0. Once we have this equation in here, we can drag it all the way across and fill out our projection all the way out to the year 20. Now, in this case, we're interested in recording the number of individuals present only after 10 years, because that's the range, the time frame that we're interested in. And so then we'll need to just retain and store those the information associated with the 10th year. What did Jed say about how do you calculate population size between years when you know what lambda is. Remember that equation. Nt plus 1 is equal to nt times lambda. So what we're going to do in this equation here is we're simply going to draw a random lambda, which we've done in the past. Draw a random lambda from a distribution whose mean is 1.3 and standard deviation is 0.4, and then we'll multiply it by the number in the previous time step, and that will give us the number in the current time step. So let's try that. We're going to write equals nt times lambda. But for lambda, we're going to go ahead and find our norm inverse function once again. We'll draw a random probability from a distribution whose mean is in cell C7 and whose standard deviation is in D7. We'll need to anchor both of those references and then press OK. Now we can copy this formula through. But there might be a problem, and let me see if we've encountered this problem here. The problem is when the population goes negative. So for example, if I had by chance drawn a very, very tiny lambda, I might have actually caused the population to go extinct. And that won't work. Negative population sizes are impossible. They just won't work in this kind of a model. So what we're going to do is go back up to our formula bar and we're going to insert another function. Let me just click off of this cell and just show you what the function looks like. So there it is. So this function is just called max. It has arguments and you enter numbers, two numbers, and the spreadsheet will return the larger of those two numbers. So we're going to use this max function and we're going to use this result as one of the arguments and 0 as the second argument. So what we're saying here is we want Excel to return either a 0 or this number, whichever one happens to be greater. So if this result actually turns into a negative number, Excel will give us a 0. And if this number is positive, Excel will give us that positive number. We wrote the word max. 0 is the first argument. This is the second argument, and now we need to close that max function with another parenthesis. And now we can copy this through and we're off and running. At this point, we can copy the formula in row 17 over to the end and then copy it all the way down through our 500 simulations. Now let's take a look at some of these results. What I have graphed here is the results of one simulation, and let me label the axes here. The horizontal axis is year and the vertical axis is the population size. So this is one trajectory, one possible trajectory when we're starting off with 84 individuals way down here. And given the random sequence of numbers we drew, these are all lambdas that are drawn from this distribution, we ended up with a population after our 20-year simulation with a little bit over 2,000 individuals. And let me change this axis here on the horizontal axis as well. So we'll choose select data and we'll edit the horizontal data so that it starts with year 0. Now if I press F9, I get brand new sets of random number and I get a new trajectory. And it looks like this population is going to do quite well because after all, it has a 30% growth rate. Each year it's adding 30% more individuals. However, by chance, given that there is some variability in the lambdas, we could end up with a lambda that is small. which would send the population down to extinction, and it will not be able to recover because of the way these formula work. Once nt is 0, nt plus 1 has to be 0 no matter how big lambda is for that year, because 0 times lambda will be 0. Let's select this graphic and we'll pull this down so that it reflects not just one series or one set of trials, but now we're getting a handle on what it looks like if we've run multiple trials. What we'd like to do now is to quantify how many of these trials result in an extinction and how many of them result in persistence. And here's where our threshold comes into play. We could say that we're interested in any population and counting a success if the population size is greater than 0. Oftentimes, however, people consider a threshold, like I want to know how many times the population dips below 25. If it dips below 25, then we're in pretty serious trouble with respect to species conservation, and maybe that's the threshold that I'm interested in. We'll be able to change this threshold later. To build this in, though, so that we're actually using the threshold, we're going to actually calculate persistence, and we'll do that over here. The ending population size is going to take into account how many years we're interested in. Let me move this figure out of the way. And I'll actually try to shrink my spreadsheet down a little bit so that we can see more of the page. So the ending population size is what we want to return here, is the number of animals in the population at the year time frame that we've specified. So I need an equation here in Excel that will return the number of animals alive in year 10, this column. And if I change this to 11, then I want the spreadsheet to return this column. We're going to use an HLOOKUP function to do this. It's another really handy lookup function, and this one, H, stands for horizontal. Here, we're going to look up the number 10, the value that's in cell G7, and we'll anchor that. And we'll specify a table, and the number 10 needs to be in this horizontal row, and the table must contain that value in the first row. So our table is going to be this table here, all the way through to the number 500. And we want it to return, once it finds the number 10, we want it to return the row, and here we want the row index to be the same as the trial plus 1. And let me explain that. Once the spreadsheet finds the number 10, it's asking you what number, I found the number 10, which row should I return? Well, we want it to return whatever trial it is, that's trial 1, plus 1 because the first row is the heading. The range lookup is the fourth argument, and we want an exact match, so we're going to enter the word false. Let's anchor the reference to the table array, and now we're ready to copy this down. And let's just make sure that this actually is accurate. So for this example, we're interested in finding the number of animals alive in 10 years, and the spreadsheet is correctly reporting those numbers here. If we change this to 9, then our spreadsheet should accurately report the 9th year, and it is. So finally, we're at this last entry here called persist. And here, I've already entered an equation here, and it just says if the population, this ending population in year 10, exceeds our threshold, then we're going to claim that the population persisted for that trial and we'll return the number 1, otherwise we'll return a 0. This formula is copied all the way through, and you can see then that some of these trials, here's one, resulted in a 0 because the ending population in year 10 was 17 individuals. And so in year 10, we record a 0 for persistence. We're almost done. We just need to calculate the total number of instances of trials in which the population persisted. However, we only want to count those trials that actually were considered in our simulation. 5. So what we want the spreadsheet to do is to count 1, 2, 3, 4. So out of those 4 trials, there were 5 instances of population persistence. Excel has a function called the SUMIF function, which allows us to sum only those instances that are actually part of the simulation. So we'll find SUMIF. The range here is going to be column B. We want to count and examine every single cell down column B, and the criteria is going to be 1. So those trials that have a 1 with them, we're then going to sum column Y. And we'll stretch our equation all the way through. So our final equation looks like this. The range is B17 to B516. The criteria is 1. And the sum range tells us what actually we should be summed. Don't forget that you can always click on these arguments and read what they're about before you press any entries. So for this particular simulation that I just calculated, the first 5 trials resulted in a population persistence. If we took this down to 20 trials, then in this next simulation, all 20 of them happen to persist. If we press F9, we'll get new sets of random numbers. There's a trial, and there's a case where 18 of the trials, in this case 18 of the 20 trials, persisted. And don't forget that we have this threshold turned on. If we drop the threshold to 0, then you would expect a greater number of trials persisting. In cell J9, we can enter the probability of persistence as just the number of trials where the population persists divided by the trials, the total trials we've run. And then the probability of extinction is just going to be 1 minus the probability of persistence. And that is our PVA. We can change the number of trials. We can change our time horizon. We can change the threshold. We can change lambda by changing the birth and death rate. We can change the standard deviation, and we can change the starting population size. All of these things will affect how these key outputs, probability of extinction and probability of persistence, are calculated and how they end up, what your conclusions will be from this exercise. You'll have a chance to play with these things and see how they affect the results when you get to the sandbox. That's where we're going to do some exercises, and we're going to play with our model and see how these different variables really drive the outcome. The other question we'll ask you to consider in the sandbox is this a reasonable model to use for lambda? For this particular population, lambda was 1.3 and the standard deviation was 0.4. But if I move this standard deviation up to, say, 0.8, now I'm dealing with lambda values that potentially could be less than 0. And we know from our equations that Jed has gone through that lambda bottoms out at 0. It cannot be 0. So a challenge question for you would be, how do you deal with this kind of situation? The way we've modeled the wolf population, we were just fine because the lambda values we considered were all positive and they centered nicely above the mean and still showed the variability that we expected. However, if your population is going to have much more variation or have a lambda that shifts everything to the left, then maybe your normal distribution's not going to be the best distribution. We'll pick that up later when we talk about it in the sandbox. So we'll see you later.